Everyone, so we just finished talking about gravitational forces, and before that, we were talking about circular motion. Now, what we want to do is bring it all together, and we want to talk about planetary motion. So, as we know, planets orbit around objects, and we know that when the planets orbit around their stars, they have to experience a circular motion, and they're experiencing a centripetal force. And the only force acting on these planets as they orbit around is a gravitational force. So this gravitational force will end up being equal to the centripetal force. Now, astronomers have been trying to figure out everything about the stars for ages. For the longest time, we were trying to figure out what was going on with all those celestial objects in the back. It wasn't until Tycho Brahe went about and took very, very careful measurements of the locations and placements of all these planets as it orbited around the sun. However, he ended up having a problem because he had all this data, but he wasn't really too sure about how to actually approach it. He was having a problem mathematically finding the link between this. Now, he had because he had this problem, what he wanted to do was find someone who could help him kind of compile all this stuff to figure out what it all meant. So he ended up getting Johann Kepler, his protege, but he was afraid that when he brought in Kepler, that if he gave him all this data, that Kepler would basically figure out what was going on, and then he would get all the credit while Tycho Brahe would end up kind of being left in the history books. Well, it ended up happening that Tycho Brahe actually died of a bladder infection, and this resulted in Kepler actually getting all of Tycho Brahe's data, and then he ended up developing three laws of planetary motion. So, ironically, Tycho Brahe ended up falling into that exact same nightmare scenario that he always wanted to try to avoid. Now, these three laws of planetary motion are pretty much like Newton's three laws of regular motion, but they're strictly for planets. And unlike with Newton's three laws of regular motion, these aren't as overreaching. Like Newton's three laws affects everything. Obviously, this really only affects planetary objects. Now, the very first law is really easy. I should point out really quickly is that just like with the other laws, you don't need to know the specific laws, especially with Kepler, since two of them are very similar to each other. But for the most part, you don't need to know, which law is which. You want to know the spirit behind the law. So the first law basically states is that every planet actually moves in an elliptical orbit with the sun at one focus. Now, this is actually extremely exaggerated because even though we do end up orbiting in an elliptical orbit, the elliptical orbit is actually extremely close to near perfect circle. It is for the most part elliptical, but it's not a something like this. Comets have more extreme eccentric ellipses when they orbit. In fact, Pluto has a fairly extreme or eccentric elliptical orbit compared to the other planets. The other planets do orbit in roughly circular motion. So even though we tend to kind of ignore the fact that it's an elliptical orbit, it is important that it actually exists. Though we're still gonna do our experiments and our questions pretending it's a perfectly circular orbit. The second law ends up saying that when the planet orbits around the star, or I should actually point out that this isn't strictly for planets around stars. This could be anything that orbits another object. So you could replace this with the moon orbiting the Earth, or a satellite orbiting the Earth, or anything like that. But as the planet moves around in its orbit, if you were to draw a line going from the sun to the planet within an equal amount of time, it will always cover the same amount of area. So in this scenario, they have this that if we just measured our location after 1 month, at this point, and then we did it the same way over here, we end up with covering the same area. This segment, this shaded area, has the same area over here. Now, what this actually means is that the speed when it's further away is very, very slow. And then when it comes around up here, it's going to be really, really fast. But the relationship between how fast it's traveling when it's really far away and how fast it's traveling when it's really close ends up being in such a way that it will always cover an equal amount of area. So its speed up here is due to the fact that, because it's closer, it travels a lot faster in order to cover more area, or an equal amount of area. Now, why is this? This question gets popped up all the time. So if you ever see a question where they ask pretty much like, why is it that the planet, ends up speeding up as it gets closer? The main answer that you will pretty much have to pick is the statement conservation of angular momentum. Now, what does this mean? You don't need to know it right now. We're actually going to talk about that when we get to the rotations unit. It's actually the very last unit in this course. So you don't need to worry about it, but if you ever do see the word conservation of angular momentum and they're referring to anything dealing with space and planets and orbits and stuff, this is most likely the answer. So I just want to point that out. There are other answers that could go with it, but this is kind of the main one. All right, so then Kepler's third law is pretty much really related to the second law, which is why I said that they're really close together. What this ends up saying is that the period of an orbit and the length a, which is the length of the semi-major axis. This is the major axis, so going from one end of the large side of the elliptical orbit to the other side. The semi-major would be this, like half of that. Will always have this same ratio, t squared divided by a cubed, being the same around any object. So for example, if we take the sun, like our solar system, if we plugged in the period of any planet's orbit and the distance, the semi-major axis distance of its orbit, and we cube it and we do this equation, it will always give us the same answer. So whether we put in Mercury's or Venus's or ours, yada, 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 Pluto, it will always give the same answer, that it's always a constant. If we go to, maybe we're looking at all the moons orbiting Jupiter, and we do, again, the periods in the semi-major axis orbit of the moons around Jupiter, again, it will be the same number. But those numbers won't be the same as what's the sun. So it's unique to whatever's being orbited. So the sun has its own constant variable. Jupiter would have its own. We have our own. All that. So this ends up being a very good thing for scientists to figure out is based off of where a planet is located, we know how long it's going to take going around that planet or that star or anything like that. I should point out one more thing about this is that the way we're going to do this is because of the fact that we're going to assume that a lot of these orbits are somewhat circular. Like we're going to assume that the ellipse is actually a circle. This semi-major axis term actually will end up being simplified as just radius, the radius of the circle. But just note that it is sort of technically different if we're talking about an elliptical orbit. All right. So going back to what I said in the beginning of this, we talked about the gravitational force being between two planet-sized objects. And we already talked about how planets and moons and satellites and all these things orbit around in fairly circular motion. And then we also talked about how circular motion causes objects to experience a centripetal force. And that the centripetal force is some other force that's causing the circular motion. So what we can do is actually combine all this stuff together into a new relationship, essentially. So what we're going to do is set the gravitational force equal to the centripetal force. And we're going to end up setting g m1 m2 over r squared equal to mv squared over r. Now, note that I'm giving subscripts to this r. As I've mentioned before, it is extremely important that you are consciously aware of the subscripts that you're using. If terms are supposed to represent the same thing, you either don't put subscripts on them or you make sure that they have the same subscript. Notice how I put RA and RB for the subscripts of R. The reason I'm doing this is because the RA, the R term in FG and the R term in FC are actually completely different variables. Now, they sometimes are the same. If we take a case where we have a star and let's say that we have the Earth orbiting around the star, assume this is a perfect circle, then the radius of the circle, which is RB, would be equal to the distance between the Earth and the Sun center, roughly at least. So they're roughly equal. So in a case like this, if we're talking about the Earth orbiting around the Sun, then these two R's would be the same and I wouldn't need to put these subscripts. However, there are times where RA and RB would be completely different. Usually, though, the way that pops out is through binary star systems. So that case would look something like this. So we have one planet here, one star there. Then we have another star, and they're both orbiting around a similar point. Now, if you look at this, we can already see why I'm making this distinction between R for FG and the R in FC. If we looked at this object, and we call that, actually I'm going to make sure I use similar notation, RB. This star is orbiting around this smaller circle. So it has a very small radius of its circular motion. But the gravitational force between it and this star is covering this full distance, which is much greater than RB. So this is when we'd have to make that difference between whether we're talking about the radius of the circle or the distance between centers. So just be very careful when you're doing this. Like I said, it doesn't come up too much where you're going to have to, worry about it a lot. But, it pops up, and just be aware of that. It's one of those perfect examples of a question where you'll see it on a test or see it in a homework problem, and you might think, oh, that's easy, and you'll just, do what you normally do. But then you should kind of think to yourself, it's a little too easy. And you want to just double check to make sure that there was no trick to what they're saying. Just double check to make sure that the two R's will be the same thing. And then also, we've mentioned this before that, whenever we're doing these things, we never really know the speed an object is when it's orbiting around. That's not something that's easy to measure. It's a lot easier to measure where it is and how long it takes to go around one time. So just like with the circular motion, we're going to end up using this equation, circumference divided by period, in order to figure out what the speed is of these orbiting objects. All right. So let's start off with this problem. Pause the video, work itself, and we'll go in a second. All right. So they want us to basically figure out the radius of the satellite's orbit using these variables. So just like before, we're going to set the force of gravity equal to mv squared of r because it's causing the circular motion. I plug in gm1 m2 over r squared in for fg. I can already see that I have m's that cross out. I have one r over here and two r's over here, so I can cross one of them out and then cross this one out. And that simplifies. When I cross multiply, it simplifies to gm equals v squared times r. Solving for r, I get gm over v squared. All right. Here's the next question. Pause the video, work itself, and we'll go in a second. All right. So once what we can notice is that we're talking about two satellites with different radiuses, and we want to know, if one of them has a speed of this, what's the other speed? So this is another comparison, which means I'm going to do the 1-1 method for this. I'm going to do the same setup that I did last time. This time, instead of solving for r, I'm going to solve for v. So this is for the speed of satellite 2. Going through the terms, the g and the m being the planet, stayed the same. So I plug in a 2 in for r, and then I end up getting that v squared equals 1/2. Take the square root of both sides, and then I end up getting this. So if you're wondering how I got v rad 2 over 2, it's that little math thing that you have to do where you normalize the denominator. So square root 2, multiply this by root 2 over root 2, and that's where you get rad 2 over 2. So just to clarify, what it should look like that. All right, here's I think the last one. Pause video, work itself. I'm going to go in a second. All right, so they want the period of the planet as it orbits around. So again, I'm starting right off the bat with this equation. I'm actually going to put in the mass of the star right into it as well. Once again, I have an m here and an m here. I have an r here and an r there. Cross that out. So I end up getting v squared is equal to 3gm over r. I'm going to plug in 2 pi r over t in for the speed. And I end up getting 4 pi squared r squared divided by t squared equals that 3gm over r. Now what I'm going to do is kind of cross multiply and move things around. I end up getting t squared is equal to 4 pi squared r cubed divided by 3gm. And then I end up getting, when I simplify, I end up getting this. All right, so I end up getting t is equal to 2 pi rad r cubed over 3gm. Actually, I want to change up how I wrote this. So if you actually notice, I wrote t squared equals 4 pi squared r cubed divided by 3gm. So I have this right now. I'm going back to what I wrote here. What if I move the r cubed over here? So I divided this out. If I look over here, 4 pi and the 3 are all constant terms. G is also a constant term. That's what it's defined as. The only other variable on this right-hand side is m. But m is a constant for the star. Like the star has some constant mass. So essentially, everything on the right-hand side is a constant term. So I get t squared over r cubed, the two variables, is equal to a big constant. Wait a minute, that was Kepler's third law. So if you recall, Kepler's third law, again, was saying that that ratio, t squared divided by r cubed, was a constant around any object. So, things that orbit around the Earth would have that same ratio for every single radius, every single distance. We could figure out what its period is based off of that. So, like I said, if we move the r cubed over, we end up getting that constant term. It's actually really interesting where it comes up. And if you ever see it on a test, you'll know how the setup is. It's setting fg equal to fc, and then plugging in the 2 pi r over t in for the speed. Just to point out, like, when would you ever use this? You might have done something like this in chemistry when you did things like with Boyle's law or Charles's law or the ideal gas law, where you kind of set the ratios equal of 2 points. You would do that here. So for example, let's say I want to know what the period is of Pluto. So I know how far away Pluto is, so I can set this ratio of the known period around Earth and the known radius or Earth radius equal to the known radius of Pluto and then solve for the period of Pluto. And I can use this known ratio and this constant variable to do anything about the objects that are orbiting the sun. So I could do this for um, comets. I could do this for asteroids. Everything will can be found using this relationship, this proportionality. I Once again, I want to mention just one last thing that's not really important for the test. It's just really extra stuff. The question is the moon falling? Now, I should have mentioned this before that the whole point that led to this discovery of gravity and the gravitational laws and Newton's three laws was that Newton actually wanted to ask himself is the moon falling towards Earth? And the answer is yes, sort of. So let's consider dropping a ball. What would that look like? Well, we know if you drop a ball, it goes straight down, right? Now, if we throw the ball, we know that it ends up having a parabolic path. So if this is the surface, it'll look like this. If we throw it faster, well, what it'll do is that it will start going further. Now, in the problems that we do, we just assume that the surface is infinitely flat and long. But as we know, eventually, if I keep throwing this ball faster and faster, eventually the Earth is going to start to curve underneath it. So there's going to be a point where we can throw the ball so fast that as it curves, the Earth curves away from it as well. And if it's maintaining that same curvature of Earth essentially, then it will continue to orbit around, never actually hitting the ground. It'll technically constantly be falling towards the Earth. So this picture kind of like just gives a nice visual that it's a parabolic path going towards the Earth, and that as we get faster and faster, the Earth starts to kind of pull away from it, causing it to fall further than it would normally do on a flat surface. So this ends up leading us to this discussion of orbital velocity. Now, the curvature of the Earth is such where 8,000 meters, after 8,000 meters, the Earth is going to drop about 4.9 meters. And it takes any object about 1 second to fall this 4.9 meters. So I can quickly figure out how fast an object needs to be in order to actually orbit the Earth, to make it so that every time it drops 4.9 meters, the Earth also drops that same 4.9 meters. Now, I want to actually mention something really quick. This is only true for this one distance. This does not mean that if I instead go out 1,600 meters, or sorry, 16,000 meters, that the Earth only drops about, what is that, 9.8 meters. The only reason I'm saying that is because this ends up being used by a lot of flat earthers who try to use, how much an object should be hidden beyond the curvature, not realizing about the way that a circle works. So I just want to clarify that this isn't really a constant thing, because by the time the object has reached 8,000 meters, it'll be at this location, but now it's moving this way, and it'll be repeating that cycle. So this is because the object is also moving in a circle, not in a straight line. So just want to clarify that. If the object's thrown at about 8,000 meters per second, then it'll end up orbiting the Earth at that speed. So some other really cool things about orbiting objects. Again, some extra stuff. You might have learned about this in Earth science, was that the moon and the sun exert this gravitational force on the Earth, and this is what's resulting in the tides. If the Earth and the moon the moon and the sun are on opposite sides, we end up getting this tidal bulge that expands out on both sides, giving us a high tide on one area and a low tide on the other. Well, it turns out that this because the Earth is spinning, the tidal bulge is actually slightly ahead of where it should be. So, like, for example, it's a little hard to see, but because of the moon's placement, the tidal bulge should be looking like this. This is where the tidal bulge should be. But instead, the tidal bulge actually acts on a slight angle above. Now, what does this actually mean? Well, what this means is that the gravitational that this ends up resulting in almost like a resistance against the circular motion of the Earth. That the tidal bulge is actually being pulled backwards towards the moon. Trying to get it back to that original orientation where it looks like this, pointed towards the moon. Now, what this really ends up resulting in is causing the water to basically create a little bit of extra friction, like I said, resisting the Earth's rotation. And it's resulting in the moon slowly speeding up in its orbit because it's being pulled upwards, pulled forward. And it's also causing the Earth to kind of slow down a bit. So the Earth ends up slowing down basically a fraction of a second every year, and the moon ends up actually getting 3 centimeters further away every year. Now, why is it getting further? Again, it's because of Kepler's third law, that this has to remain constant at all times. So if it's getting faster, its period is increasing, therefore its distance, its radius from the Earth has to also increase. Now, if this continues to happen over millions and millions of years, eventually it'll get to the point where even though the Earth is orbiting, the bulge will end up pointing towards the moon, because we'll get to a point where the Earth will actually rotate with the moon. So the moon and the Earth will actually rotate together. After this rotates one full day, the moon will also rotate one full day. Uh, this is actually a very special name. It's called geostationary orbit. It'll be pretty cool. Obviously, we won't be around at the time, but it will basically mean that there will be one place on Earth where you'd have to go in order to see the moon, and that if you weren't at that location, you wouldn't be able to see the moon anywhere else. All right, that's it. Like I said, this whole thing is, how do we combine this, what we've talked about with circular motion, and relate it to what's going on in space. In the next video, we're actually going to talk about the last thing with circular motion, which is actually probably one of the, I want to say it's the trickier ones, but it's really not that tricky as long as you continue with everything that I've mentioned with forces, approaching it the exact same way with the FBDs, with the sum of the forces, yada, yada, yada. We're going to end up talking about moving objects in a vertical circle. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.